So the way that I decided to handle functions was by dividing the semantic checks into two categories. Ones that couldn't be done until the function scope has been resolved, and ones that can be done without resolving the function scope. And most of them fall into this category, but there are a couple that can be done in the main parser.y file that usually involve accessing the global symbol table. For example, making sure that a function name doesn't already exist in that symbol table. As for trying to handle semantic checks when the scope needs to be known, my initial approach was to try and see if I could pass down the function scope to the different production rules. So passing the identifier for the function declaration down to the different statements so that the semantic checks could just be done immediately there. But I wasn't able to get that to work. So instead I opted for putting off processing all of the statements and putting them onto a stack, and then processing them once I reach the function declaration. And so to manage doing that, I created an instruction struct that contains all of the different data that I need to process the semantic checks. So, for example, what type of production rule it is. So maybe it's a variable declaration or a parameter declaration. And then I might also pass along data such as the identifier name and the identifier type. And here's an example of that. So for an array, I would pass the identifier name, that it's an array type, the type of an array it is, and then the instruction type, so it knows which function call to make to process that. So to go into more about how functions work, for a function's block, all of the instructions within the block are put onto the instruction stack. And then when the parser recognizes a function declaration, those instructions are copied to an instruction symbol table, which is attached to the function's symbol table. And then when a function call is made, the parameters are copied onto the instruction stack, processed, and then the function's instructions are copied onto the stack and then processed. And that is done for each of the different function calls, but specifically for the main, rather than trying to store those instructions into a main table or global symbol table, I just immediately call to go and process all the instructions in the main. So to talk more about the AST generation, before adding this instruction stack, all of the AST nodes were built in the parser.y file. And this is still somewhat the case, where there are production rules where the AST node is entirely handled in the parser.y file. But now there are cases where the AST nodes need to be modified when processing the instructions. So for an example of this would be the function's return statement. I might declare that the function has a return node with some constant value, but I'm not going to assign any value to it initially. Rather, when a function call is made, in those instruction processing statements, it will go and assign the value to the AST node. And the way that I do that is by also passing AST nodes in my instruction struct that are relevant to the semantic check processing and function processing. And here is an example script. I do have it where function folding works. So functions that don't have any dependencies in them, such as like a write statement, will automatically be folded, and rather than going and calling the function, it should just assign the value. And I don't have it entirely removing the function, which would be ideal, but it does remove all the statements within the function block, which does provide some optimization. And then here's an example of the script running. So in the Lexer, I have conditional operators and Boolean literals to help to recognize conditional expressions, which I have added production rules in the parser for. And these conditional expressions are used by both the while block and the if and if else block, or else if block. For AST node generation, it looks something like this, where for if and if else rules, it generates a node for the conditional expression and a branch node that contains the instruction block. And then if there is an else if or else statement following that, that's stored in the right side of the node. So right now, the IR code is generated solely from the AST nodes. So when a branch is encountered, it creates a label for the type, which I store as, or in the AST node, such as if, else if, or else. And then if it's if or else if, it also creates a condition at the top to branch to that label. So I wasn't able to get the parameters for those conditional blocks working because there were a couple issues. So the main idea was to try and slightly modify the way that functions were handled to handle them as conditional blocks. So for functions, it would be setting the function parameters, processing the instructions within the symbol table, and then it would expect a return, and it would set the return at the end of the function call. But for conditional blocks, you expect to have access to everything within the current scope. So that would mean setting for parameters everything within the symbol table. And then it would just be the same as functions for processing instructions. And then you wouldn't expect any return. So the issue with trying to do this is running out of registers, which can slightly be solved by identifying which identifiers or parameters within the symbol table are needed within the conditional block. So they would be dependent on what's being executed within the conditional block. So maybe there is some variable being modified that is then printed after the conditional block. But even with trying to do this, we would still be running out of registers because we don't have any structure in place to allocate and deallocate registers to variables or values when they are used. And I wasn't able to find a workaround that wouldn't involve modifying most of our system. The setup for identifying in-use registers and allocating and deallocating registers was kind of something that needed to be done more near the beginning before upscaling. So now this kind of makes it more difficult to implement. So to go over how the compiler works in its entirety, I've already gone over the instruction stack and how that relates to functions in a previous Loom video, so I'm just going to go over that briefly and then talk about the other components. So our compiler divides semantic checks into things that can be done without the scope being known and things that cannot be done without the scope being known. So things that can be done without the scope being known are immediately processed in the parser.y file. And then things that can't be done until the scope is known, because we couldn't get the scope to be passed down as the parser is bottom up. We put all of the relevant information into a struct that we call an instruction struct, and then we put that onto a stack of instructions. When a function is declared and that rule is recognized by the parser, then all of the instructions currently on the stack are copied to an instruction symbol table, and that's used to be able to read the instructions for a function, which helps the process when you call a function multiple times. And then when a function call is made, parameters for the function are copied onto the instruction stack processed, and then the function instructions are copied onto the instruction stack, and then the function scope is resolved. So all of the instructions within the function. So in order to modulate different components of our compiler so that we could work on different components separately without worrying, for the most part, that modifications would affect each other, I decided to go with trying to do a multi-pass system, similar to how the lexer passes data to the parser and then the parser processes that. And then to trigger all of these passes to happen, I just include them all in the program grammar rule. So when the global block list is recognized, then it goes ahead and goes through all the different passes. So the first pass that is done is the liveliness analysis. Then the IR code is done. And then we have another pass after the IR code pass to inject the parameters into the IR code text file. And that's to handle function calls. And then afterwards, the IR code is then converted to MIPS code. So the liveliness analysis is something that is unique to, or is managed in the symbol table and is unique to each scope. So whether or not a variable is alive in one scope doesn't impact whether or not it's alive in another scope. So during the initial pass, where the instruction stack in the parser is being handled, each time a variable is referenced, the number of instances is incremented. And then each time a variable is folded, the number of instances is decremented. So this is constant folding, where you replace the value of a variable with its constant representation. So for example, if you declare int x as 5, then it can be folded in the following line where x equals x plus 3 and on the right side of the equation. And then after the initial pass, another check is done to catch unused variables which don't get caught using the prior method. And then whether or not a variable is alive or dead is determined by whether the number of references to the variable is less than or equal to 1, which corresponds to dead, or greater than 1, which corresponds to alive. So specific instructions that act as an output will use the increment variable in the symbol table for the liveliness analysis, independent of whether some variable can be constant folded. as the end goal is to optimize code that outputs to the console. So to give an example of this, the write statement increments the number of variable references where we could replace x with its corresponding value in the symbol table. And then here's where that is done in the instruction stack processing. The second pass, writing IR code to files, is for the most part handled purely by recursively iterating over the AST. And as mentioned in the previous video, sometimes we might build a base for the AST nodes in the parser.y, and then when the instruction is processed, those nodes are edited and filled in. So recursively iterating over the AST to build the IR code and purely relying on that means that we have to make some modifications to our AST beforehand. And to give an example of that, I have a node that isn't created in the parser.y file, isn't assigned to anywhere in there, but it's called node block parse, and it's purely for the IR code processing. Where if it hits a block parse node, then it will return and not continue to parse down the remaining tree. And that is mostly relevant for how we process write nodes, where if there's a write node, then we move all of the assignment statements to the right side of the write mode. But it still exists within the main scope node. And here's kind of an example to show you what I mean. So you can see here that kind of the same thing is duplicated within the AST, where this assignment statement is just copied to the right side of the write node. So without the node, to continue what I was saying, without the node block parse, this assignment statement would get duplicated in the IR code. And then the handle IR code for parameters pass, what that does is it goes through the IR code, and with the first pass of the IR code, there are inserted keywords for parameters so that this pass can go through and recognize those. So what this does is that when it recognizes that function call, it checks if a parameter is alive. If it's not, it's going to remove it from that IR code. And then the conversion from IR code to MIPS is kind of handled in a similar way to how the parameters are handled, where it's just reading over the already created text file and matching symbols to create additional text. So whereas the parameters would maybe insert or delete the parameter, this would add text to another file for the MIPS code. And this is what Rylan was working on. That just gives a basic overview of how it functions.